In the previous videos, we've seen how we can approximate the value of the derivatives based on the value of the function at points on the grid. In this video, we're going to put all of this together to approximate the solution of a PDE. Or actually, I should be saying of an ODE, since obviously we will be in dimension 1. So let's consider this ODE minus u second plus cu equals f on an interval 0, 1 with Dirichlet boundary conditions u of 0 equals 0 and u of 1 equals 0. F will be a continuous function and c will be a continuous function that has its values in R+. Now, we have already discussed the existence and uniqueness of the solutions to this equation. We did that during the lab session, and we saw that, well, there is a solution. The solution is unique, and it is in C2. So we have the regularity of the solution. Now, let me consider a mesh of the interval 0, 1. So we'll consider a uniform mesh, and I will have x naught equals 0, xj plus 1 equals 1, both ends of my interval. I will have j plus 2 nodes all together, boundary included, 0 and 1 included, and j nodes inside, which means that I will have j plus 1 intervals, and of course h, which will be 1 over j plus 1. I will define the value of c at xj. I will define this, I will give a name to this, and I will call this cj. That will be the value of the function c at the point xj of my grid, of my subdivisions. And the same thing for fj. Fj will be the value of f at the node xj. Now, I will consider uj, and these will be the unknowns that will approximate, hopefully, u of xj. So these will be the unknowns, will be the uj. Now, there are two u's that I know. There is obviously for x equals x naught, well, I know that u naught is equal to 0. It's even better than an approximation at this point. It's the exact value because I have the Dirichlet boundary condition, right? So that's one value of u that I know. And of course, the other value is at the other end. I know that u of 1 is equal to 0 as well. So the first thing I know is that u0, the approximation, the approximation of u on the first point of the grid is 0. And it's even better than the approximation, it's actually the exact value. So let me write this up here. I'll keep this on my board and I'll see what else I know. Well, I have some information about x1. Right? I know that minus u second x1 plus c x1 u x1 is f of x1, right? This is coming from my ODE. So I just have this. Now, the second derivative at x1 can be approximated using points on the grid, right? This is what we did in the previous video. So I can replace u second of x1 by a finite difference quotient, obviously second order. Cx1, I know the value as a name, C1, and Ux1, well, I have an approximation, that will be U1, and f of x1, that is f1. So let me replace this, everybody, but it's by whoever should replace them. Here's what I get. So I have my second order quotient here. Then I have my C1, U1, then I have my F1. So here's what I obtain. Of course, I know that U0 is 0, so I can already remove that U0. I can even change and remove that negative sign. Let's just change the sign here. So here's what I get. And let me actually factor U1. So what I obtain is 2 over h squared plus C1 times U1 minus 1 over h squared U2 equals F1. Okay, so let's keep this. Let's write this here. And let's move on. So I'm going to go from x1 to x2. And, well, I'm going to do exactly the same thing. I mean, I know that, well, x2 is in between 0 and 1 in the open interval, so I can actually apply this PDE or ODE for x equals x2. I'm going to replace the second derivative by the quotient, and the C2U2, then an F2. Okay, so here's what I obtain. And then I'm going to rewrite this way. Minus 1 over h squared u1 plus 2 over h squared plus u2 times u2 minus 1 over h squared times u3 equals f2. Now, if I went too fast, I suggest you stop the video, rewind a little bit, and make sure that you understand every single line of the computation. It's important that you really need to understand what's going on here. All right, so let's keep this equation here. And let's basically see what is going on in general if I consider x equals xj. So j will be in between 2 and j minus 1. Well, I will put in xj in my equation, and I will use the difference quotient to approximate my second derivative, as I just did a few times already. Then I will replace cxj by cj and the right-hand side will be fj. So here's what I obtain. And let me actually put this, in this form. Then I have minus 1 over h squared uj, minus 1, plus this coefficient, which is 2 over h squared plus cj uj, minus 1 over h squared uj plus 1 equals fj. All right. And, well, let's see what happens when we get to the other end of the spectrum. Let's see what's going on, for instance, for xj. So for xj, I'm going to, again, do exactly what I did several times. So I'm not going to emphasize that. I'm just going to go a little faster. So here's what I have. I'm putting things together. Of course, uj plus 1 is u1, which is 0. So I just remove that term. And here's what I obtain. So when I write it this way, I have this equation, which I'm going to keep here. Finally, I get to the very end of my spectrum, and that's uj plus 1, which I know is 0. It's even better than an approximation. It's the actual value of u of 1. Okay, so I have a system here, a system of equations. It's a linear system. And as a matter of fact, I kind of want to write things in a matrix form. So let UH be U1 to UJ, U1, U2, all the way to UJ. That's J components. And I'm just writing it in line, and I'm putting a transpose. So the star here means transpose. I'm just doing this because I'm running out of space on that slide, so that's why I'm doing it. And FH will be, again, that column vector F1 to Fj, and I'm writing it with a line with a star because it's a transpose of that line vector. So that is Fh. And then I will consider the matrix AH, which will be 1 over h squared with, well, basically 2 on the diagonal, -1 on top of the diagonal, and -1 below, and zeros everywhere else. And CH, which will be this diagonal matrix, well, the diagonal terms are C1 to Cj. Now, if I write things this way, then what I have, the system I have, the linear system I have, can simply be written as AH plus CH, that's this matrix, AH plus CH. In other words, it is the matrix AH to which, on the diagonal, I basically added C1 to CJ, times UH, which are my unknown, is equal to FH. And obviously, U0 and UJ plus 1, which are known, they're not unknown, they're known, are equal to 0. So if it's not clear for you why we have this equivalence, I strongly suggest at this point you stop the video and you make sure you understand why we have this equivalence up there. Okay, now that we have written our system of equation as this, then what I'm going to say is that all we need to do at this point is to solve for UH, right? AH plus CH is a matrix which is known. I mean, AH is known, it's written right here. CH is known, it's written right there. Well, you still need to evaluate your function C at the points of the grid, but that's not something that is difficult to do. And FH, well, obviously, that's, again, the evaluation of F on the points of the grid. That's not very difficult to do either. So what I'm saying is FH is known, AH plus CH is known, so all you have to do is to solve for UH. Well, you still need to verify something. You need to verify that AH plus CH is non-singular, and when that is the case, then, well, obviously that system will have a unique solution. So theorem for j greater than 1, the linear system AH plus CH, UH equals FH has a unique solution UH, and obviously the proof is, well, we need to verify that AH plus CH is not singular. So let's do it. Let's just to simplify the notations, let's call B AH plus CH. I'm dropping the H for now because it's just easier this way. And I'm going to consider a vector V of dimension J, which what I'm going to verify is that B is a definite positive matrix. So, and by the way, it will also be symmetric, but I mean, at this point, I'm just going to verify it's definitely positive. So, so to do this, what I'm going to do is I'm going to consider V transposed BV, or if you prefer, V inner product with BV. That is the sum for I equals 1 to j of VI, BVI. I mean, that means that the ith line, the ith component of V and the ith component of BV. B is a matrix, V is a vector, so BV is a vector, and the ith component, the ith line, if you prefer, of BV, I just basically multiply these two. So that's not very complicated. I mean, you know how to do linear algebra. Now, I'm going to replace that BVI by simply the sum for k equals 1 to j of BIK VK. And I'm going to treat separately what happens for I equals 1 and I is equal j. So let me actually just rewrite this sum by sum for I equals 2 to j minus 1. And then I will pull out this 2, what happens for I equal 1 and I equal j. So for I equal 1, I have V1 sum for k equals 1 to j of B1k VK. Now B1k, if you look at the matrix down here, the matrix, well, B11, we know the value of B11. We know the value of B12, but B13 and all the rest of the values will be 0, right? So really, I can replace this by V1 times B11 V1 plus B12 V2. Same thing happens for the other term here, Vj. Look at the matrix over there. What happens? Basically, all the terms of that sum will be 0, but for the two last ones. So what I have is Vj, Bj minus 1. So it's not a product here. It's line j, column j minus 1. Vj minus 1 plus Bjj Vj. And what I did for these two terms, I can somehow do the same type of thing for the first one, right? I mean, look at what we have in the middle here. Sum for k equals 1 to j of B I k V k. Well, basically only 3 terms will be not 0. So let's actually just replace this sum by that sum. Okay, and let me actually just rewrite it with the actual values that we know we have. So I'm just replacing these things here in the sum, and I'm doing the same here for that second term, and I'm doing the same for this last term. Okay, now let me actually just, well, just make the computations like this, and let's actually write everything like that. So what we eventually obtain is this. And I'm going to separate the sums. And by separating the sums, you can see that I can actually just simplify things a bit. And I obtain, well, minus sum for I equal 2 to j minus 1, Vi minus 1 Vi, plus the sum for I equals 1 to j of 2 plus ci vi square minus sum for I equals 2 to j minus 1 of vi plus 1. And we had two terms that we could not reincorporate in, and that's minus v1, v2 minus vj minus 1. Now, let me make a change of index here. I'm going to write I prime equals I minus 1. So that first sum, I can really replace it by the sum for vi prime plus 1 for I prime going to 1 to j minus 2. If that's not clear, just write the values we had. Obviously, we started with v1, v2, and we ended with vj minus 2, j minus 1, and it's still the same here after changing I minus 1 in I prime. And of course, I can just drop the prime because I can call my summation index the way I want. So I'll just call it I. It doesn't really matter. Okay. Anyway, what I have here, and the reason why I did that is because I can actually, I will be able to simplify things with the third sum. So basically, what I'm saying is first, let me reincorporate the two missing terms here into the sums. I mean, obviously, I have two terms that are kind of trailing behind, and I can reincorporate them into the sums provided I change the boundary slightly. So here's what I get. I get three sums, and that's what I obtain. Okay, now what I can do is to put these two sums together, and I obtain basically sum for I equals 1 to j of 2 plus ci vi square minus 2 sum for I equals 1 to j minus 1 vi plus 1. Well, actually, let's just separate in three sums this sigma. I mean this first sum. And what I obtain is my ci. Then I obtain the vi, and then I obtain the vi which I put on the other side because I'm going to change the index again. So let me actually first move this vj away, and then I'm going to change the index. And by changing the index, I have the sum for I equals 0 to j minus 1 of vi plus 1 square. So actually, because I don't want to have I equals 0 to j minus 1, but I prefer to have I equal 1 to j minus 1, let me actually move out this v1 square from that sum. And as you can see, I'm quite happy because what I have is the sum of v1 square minus 2v1, v1 plus 1 plus v1 plus 1 square. And all these three terms are together in the sum. And the two trailing terms obviously are not in the sum. So, and obviously these three terms are basically simply vi minus vi plus 1 square. So what do I have? Well, obviously I have, everything is positive. That's the first thing. I mean, obviously when I do v transposed bv, that is, that's non-negative. I mean, you have basically all the terms here are non-negative, so that's the first thing. And if you have transposed of v, bv equals 0, well, it means that v1 square has to be equal to 0, vj square has to be equal to 0, and all of the ci vi square also have to be equal to 0 because ci, as we know, is positive. And by the way, if ci was to be equal to 0, then I could still recover the fact that the vi's are equal to 0 based on the second sum simply by a pretty obvious induction. So what I'm saying is that, the matrix that we have is definite positive. And as a consequence, it is not singular. All right, so that was really a little bit of linear algebra. And we'll see that obviously linear algebra is going to be a key component in the finite difference method. It was already a key component in the finite element method, and this is why in the next chapter we're going to go into linear algebra again, and we'll actually even see how we can do linear algebra efficiently with a computer. So that's the next chapter, but obviously, as you can see, this is something that we need. All right, so we have proven the theorem. This equation, AH plus CH UH equals FH, has a unique solution UH, and this will be called, this matrix AH will be called the finite difference method matrix of the Laplacian in dimension 1. So if basically you have C equals 0, then CH can drop CH, and you have only this this matrix AH. And as you saw in the proof, I did not, I said, if CH is a 0, then we can still recover it by that second term. We could still prove the non-singularity, the positive definiteness, and therefore the non-singularity thanks to this. I'm going to finish this video with something that we talked about before called the maximum principle. To do this, I'll need to introduce what is a monotone matrix. And to introduce what is a monotone matrix, I need to introduce what is a non-negative matrix and what is a non-negative vector. So here is the first definition. We say that a vector V is non-negative if all of its components are non-negative. We just note V greater than 0, even though we don't know what it means. Same thing for a matrix. We'll say it's non-negative if all of its components are non-negative. Now, a monotone matrix is a matrix M such that for all vectors V such that MV is non-negative, then V is non-negative. So necessarily V is non-negative. If that's the case, then the matrix will be called monotone. Now we have two lemmas that are interesting. The first one is that if you have a monotone matrix, then it is not singular. You can invert it. And by the way, you can invert it, and this inverse will be non-negative. And it also works the other way around. If you have a matrix that you can invert and it is non-negative, then the matrix is monotone. So that is, these are two interesting lemmas that will put the proof on the website. And by having these two lemmas, we'll actually be able to provide this maximum principle that we're going to talk about in a few seconds. But before we do that, I would like to point out that AH plus CH is monotone. We'll do the proof in the lab session. Now, because of this, if FH is non-negative, then AH plus CH UH is non-negative, right? Because that's FH. And by assuming that, by considering the lemma that said that it is that AH plus CH is monotone, then that implies that UH is non-negative. So here is the maximum principle theorem. If F is non-negative, then UH has only non-negative components. And I said that we already discussed the maximum principle. We did that in chapter 4. I said at the time then what it meant is that when I turn on the heater in a room, then basically the temperature rises. And what I suggest you do is you go back to this chapter and you understand how this compares to the maximum principle that we're studying today.